Good afternoon to everyone. In today's video, we are going to see the derivation of EMF equation of a transformer. So here we know few things about the transformer. Transformer is a static device. Transformer is a static device which is having two windings. So the first winding we called it as a primary winding, which we excited within a source, and the second one is the secondary winding where we connected the load. Here there is no electrical connection between the primary and secondary winding. There is only the magnetic coupling between your primary and secondary windings. We call that one. Okay, so because of the induced EMF from the primary winding to the secondary winding, the EMF is induced in the secondary winding and will be circulates the current to your load. So what will be the EMF induced in your secondary winding or primary winding? We are going to be seeing. Okay, so here the primary winding is excited with an AC source. Okay, so the same thing I'm written. The primary winding is excited with an AC source, and that EMF, that means that voltage will be responsible for the circulating the current, because the primary winding is closed circuit right now. When you consider this one, it is responsible to flow the AC current, because you are providing the AC voltage, so it will be produces AC current. And due to this current, when the current is flowing into a coil, automatically an EMF is a flux is generated in that coil. So this flux will cuts its own coil, that we call it as self-induced self-inductance, and the same flux, if it cuts the other coil, we call it as mutual inductance. So mutual inductance is the principle behind your transformer working. Okay, so whenever the flux in the primary coil cuts the secondary coil, it induces an EMF. Okay, the same thing we provided. So when an alternating flux cuts its own winding, that means it induces an EMF of E1. And if it cuts the secondary winding, it induces an EMF E2. It induces an EMF of E2 in the secondary winding. So this EMF is called mutually induced EMF. So here we are providing the alternating voltage for the primary winding. Because of that, we are getting the alternating current, so that it produces an flux, which is also an alternating one. So the flux produced in the coil is alternating one. So alternating is nothing but represented in a sinusoidal format. So this is your flux waveform. When you go through this waveform, the positive and negative peaks of flux will be represented with phi m. So this is a sinusoidal waveform, so it is given in the expression of phi equals to phi m sin omega t. And here, to complete this entire one cycle, it takes the time period of 1 by f. For completion of half cycle, it takes 1 by 2 f seconds. Similarly, 1/4, it takes around 1 by 4 seconds of time. Why you are needing this thing is nothing but during at which time you are having the change in flux, we are going to be seeing. So when you go for the terminologies, so phi is the flux, phi m is the maximum flux, and whereas n1 is the number of turns in the primary, and n2 is the number of turns in your secondary. Similar fashion, the f is the frequency of your supply voltage, and E1 is the RMS value of induced EMF in the primary winding, and E2 is the RMS value of induced EMF in the secondary winding. Kindly consider these are the RMS values. Okay, so as per your Faraday's laws, of electromagnetic induction, the average EMF induced in each turn is directly proportional to the rate of change of flux. Rate of change of flux is nothing but d phi by dt. Change of flux, rate of change of flux, at what variation it is going to be changing, at what variation it is. Simply I can call it as a slope, d phi by dt. On x-axis we have the time, on y-axis we have the, so this is the slope, dy by dx. So the average EMF per turn will be equals to the d phi by dt. So d phi is nothing but change in the flux to the change in time. So here already we seen in 1/4 of second, I have the flux is varying from 0 to 5m. So I can write this one as from 5m y2 minus y1 divided by x2 minus x1. x2 is nothing but 1/4f and x1 is 0. Similar fashion, y2 equals to 5m and y1 equals to 0. So d phi by d1 it will be equals to 4f 5m Weber per second, because flux is measured in Webers and time is in terms of seconds, so Weber per second. So this is the average EMF per turn, So you may ask the question, here you written the Weber per second, whereas coming to here it becomes volts. Kindly observe, EMF is nothing but the voltage, so voltage is measured in terms of volts, so Weber per second or volts both are be similar. So here this is the average EMF per turn. So in the primary I am having N1 turns, and similar fashion in the secondary also I am having N2 turns. I can consider average EMF of primary will be 4f 5m N1, and similar fashions for secondary 4f 5m N2. Okay, right now I am having the average EMF, but I am considering the E1 and E2 for the RMS values. We should know the relation between your RMS and average values from the form factor. So for sinusoidal quantity, the form factor equals to 1.11. So the relation between your RMS and average values are nothing but RMS values equals to 1.11 into average values. So I converting this one as RMS value of induced EMF equals to 1.11 average value of induced EMF. Already I know the average value of induced EMF 4f 5m. Okay, I simply substitute that one to find out the RMS values. So the RMS values of induced EMF is 4.445 f 5m volts. For primary side I will consider for N1 turns, and for secondary I will consider the N2 turns, because previously it is per turn. Okay, so this is the expression for the induced EMFs of primary and secondary windings. Okay, I hope this will be useful for you. Thank you.